In this section, we're going to learn about hybridization, which is actually a concept that helps us understand why molecules adopt the shape they do, in addition to what VSEPR or Vespers theory dictates. So if you remember, bonding requires there to be some orbital overlap. So generally speaking, whenever two atoms are going to bond together, part of the reason why they bond is because the electrons that are located in these orbitals, they can interact and pair up as long as the orbitals overlap. So you can see here some examples. Hydrogen and hydrogen, right? Each of these has one nucleus or one proton in the middle. That's kind of representing the nucleus anyway. It doesn't really matter how much is there. But then, you have these electrons that are floating around, neither of which, again, are in any specific place. But again, when they come closer together, find that sweet spot, right? Those pairs of electrons, they'll locate in between the nuclei, right? They'll be there in that overlap region. Same thing with the hydrogen and chlorine. If these two were to bond, right, independently, right, hydrogen would bring in one electron here. This is a single orbital that chlorine contributes that has an electron. And again, that will also overlap with a hydrogen, and that's where the bond, again, is located. And then finally here for this one, right, same thing, chlorine atom, probably red on red is not the best idea, so let's try and use green. And you see that those will overlap, where this chlorine right here individually would have an orbital that kind of looks like that. This right here would have another 3p orbital that looks like that. You'd have a green one floating around in there somewhere like that, a green one floating around somewhere like that. And of course, these can sort of turn and twist and spin around. And then that's where you eventually find that these two are overlapped to be paired up right there. Now, the problem is those are actually what we call atomic orbitals, right? So we think of these as orbitals that are associated specifically with an atom. But when we talk about bonding orbitals, like when they come together and now start interacting with each other, it actually kind of has some other factors that are involved. Let's go and see how this is arranged. First of all, atomic orbitals are a free atom, especially the ones that are the p orbitals. Those are aligned with the x, y, and z axes. So in this language, we're going to look at carbon, right? We're talking about carbon specifically. We have an atom that has, you can see this black area. That's going to be your 1s orbital. This right here, this outer one is kind of a fainter orange one. That's going to be your 2s orbitals. And then your p orbitals, your 2p. You have a 2p right here and a p orbital like this and a p orbital like that. So those, again, are all 90 degrees from each other. But if you have a carbon atom that then engages in bonding to make CH4, right? Then you have C, you have an H, 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 and H, right? Well, you actually don't really have this sort of 90-degree arrangement anymore. So this, again, while we draw it out like this, and we might visualize this as having these orbitals that are along the X, Y, and Z axes, those bonds, when those atoms, again, engage in bonding, you don't actually end up seeing 90-degree angles from each other. They're actually 109.5 degrees from each other. So what's going on here? Again, how do we reconcile this mismatch? We have a free atom of carbon, which has these very rigid XYZ axes arrangements, versus the bonded atom of carbon, where it engages in bonding. All of a sudden, it takes on these non-90-degree angles. It takes on 109.5 degree angles. So where does this show up? How does it happen? And that's where we introduce something called hybrid orbitals. Hybrid orbitals, again, effectively are where we take the atomic orbitals, right? So there's very rigid S's and P orbitals that we just saw, like, for example, in carbon. And they're basically reorganized and then reshaped into something called hybrid orbitals through a process called hybridization. So again, atomic orbitals undergo hybridization to become hybrid orbitals. One more time, atomic orbitals undergo hybridization to become hybrid orbitals. So these atomic orbitals, as they get rearranged, how that happens doesn't really matter per se. The important thing is that we sort of recognize that there is a change that occurs. And so those 90-degree atomic orbitals of free carbon are kind of then rearranged and reshaped. How exactly, what the nature of that is, we don't really know. At least we don't need to know at this level, but just recognize that it does happen. And that's where that 109.5 degrees then can show up. And that's what we see right here. Both of these, again, represent hybrid orbitals. So this has already been hybridized. This has been hybridized. These are all hybridized. So these, again, the ones that I'm showing you here, these have already been changed and converted into orbitals that can engage in bonding, or that are going to engage in the bonding. This right here, again, shows you that you have now added hydrogens. So it's the same sort of setup here, but you have the extra added hydrogens that are then going to bond with those hybrid orbitals of carbon. Notice how this hybridization focuses on the central atom, doesn't really notice or doesn't really care so much about the outer atoms. Now, what I'm about to introduce to you here is sort of a little visual. The actual nature, again, of how this works isn't as important as just recognizing the pattern that we're going to go over. But to start off here, we're going to talk about something called sp3 hybridization. sp3 hybridization. So what we're going to do is we're going to take a single s orbital and 3 of the p orbitals. Those will together combine and be hybridized to become the 4 sp3 hybrid orbitals. So again, 1 s orbital, 3 p orbitals to become 4. So 1 plus 3 gives you 4. And specifically, because we're taking 1 of the s's and 3 of the p's, we actually have this sort of terminology or this sort of label, sp3 hybrid orbitals. On the right side, we kind of see what happens here, right? So this is the s orbital. These are the 3 of the p orbitals, right? So p orbital, p orbital, p orbital. All together, those get kind of mashed up together and then spit back out, right? So when they get spit back out, they get to form these new hybrid orbitals, and there's 4 of them. And each of them has the designation of sp3. This is another sp3. There's a third sp3. There's a 4th sp3 hybrid orbitals. And again, since these are not actually independent, isolated hybrid orbitals, right? They're actually all part of one atom now that's being able to bond. That is, again, part of this whole thing. So all put together, you have your nucleus in the center, and then you have each of these sp3 hybrid orbitals coming off, and you notice they give you the 109.5 degree angle, meaning this is going to have the tetrahedral arrangement. So individually, these do not have tetrahedral arrangements. You smush them up and spin them back out, you get yourself some tetrahedral, and that's how sp3 hybridization works. As a side example, sp2 hybridization, you can kind of see where this is headed, hopefully. You have 1 sp orbital. You take 2 p orbitals. They hybridize, combine, spit back out as 3 sp2 hybrid orbitals. And so what happens here again is that you have a single s orbital, you have a p and another p orbital. Those are all mashed up together, and then they're spit back out. It undergoes hybridization, and then you get one that looks like that, another hybrid orbital looks like that, another hybrid orbital looks like that. This is a single sp2 hybrid orbital. This is a single sp2 hybrid orbital. This is another sp2 hybrid orbital. And all together, right? So this is not an individual, like these are not individual orbitals. These all together form this sort of triangular shape, which makes sense because, again, that's the 120 degrees that you might see of certain things that have sp2 hybridization. So you might have heard some of this kind of connection that I'm making. And while all that, again, it's a lot, the main thing is that you kind of just recognize that the s's and the p's, the reason why they're called sp3 is because they come from a certain number of s's and a certain number of p's. And the best connection, the easiest thing to do is really just focus on this slide where it establishes the pattern, where you don't really need to know the individual details necessarily like I just went over. Just know that you have this pattern. So again, we're focusing on the hybridizations of the central atom. You have these possible hybridizations. So these are only 5 that we'll see: sp, sp2, sp3, sp3d, and sp3d2. So what they're saying is that each of these has, or each of these tells you exactly what orbitals were used to make them. This one, for example, was 1 s orbital, 3 p orbitals, and a single d orbital all mushed together, spit back out to make these sp3d. So here's how it works. For any given covalent compound, you can determine the hybridization by first determining the number of electron domains around your central atom, which is something we've had plenty of practice on so far. And then also matching the number, whatever that number is, with the sum of those superscripts of those hybridizations from above, so from up here. Let's see how this looks in practice. NH3. All right. First of all, in order to know the NH3 electron domains, you probably need to draw the Lewis structure. So this one is pretty easy. We've seen this a couple times now. And we've got ourselves 4 electron domains, right? We have 1, 2, 3 bonding ones. We have a single lone pair. That's a total of 4 electron domains. And then I'm going to match that with the superscripts that are all on these hybridizations up here. So we actually see on this one, right, we have an S, that's a superscript of 1, P3, that's a superscript of 3, 1 plus 3 is 4, which matches the 4 here. So for NH3, the hybridization will be sp3. This next one, NO2 minus, again, I'm going to skip ahead a little bit, just going to help you out with this one. I know that this is going to have this kind of a Lewis structure, and, excuse me. So based on this structure, right, we have how many electron domains around the central atom? We have 1, 2, 3 electron domains. And so that ends up being sp2, right? sp2, because S, superscript 1, P2, superscript 2. That's a total of 3 right there, the superscripts, and that corresponds to the 3 electron domains that are around the NO2 minus. All right. Even if you don't really exactly understand how hybridization works or what the nature is, go ahead and try this practice out. You should be able to identify the appropriate hybridization with the central atoms of each of these other examples. That'll do it.